Welcome to the second part of Novinium's Smart Monitor webinar series. Today's topic is leveraging real-time data collection. My name is Chrissy, and I'll be your moderator for today's session. Before we begin, I would like to let you know that we encourage you to submit questions that you may have into the chat window at any time during the webinar, and we will address them during our question and answer session. If you would like to share the information presented today or go back to attend again, a recording will be available on our website afterward. I'd like to introduce today's speakers. We have with us Branko Horvat, Director of New Product Development, and Lee Getzwich, Engineering Project Manager at Novinium. Branko Horvat leads all aspects of the Prevent business, including engineering design, business strategy, technology development, and logistics. Before joining Novinium, he held a number of leadership positions in the mobile hydraulics industry, and he has been awarded several patents related to hydraulic control and design. He holds a BS in Mechanical Engineering from Milwaukee School of Engineering and an MBA from Iowa State University. Lee Getzwich is an Engineering Project Manager at Novinium with a focus on new product development. Lee has 2 decades of product line management and new product development experience at Seattle area companies, including Romac Industries and Cascade Designs. He holds a patent or patent pending on 5 product designs and a BS in Mechanical Engineering from Lehigh University. And without further ado, I will hand the presentation over to you, Branko.
Thank you, Chrissy. It is a pleasure and privilege to be part of this webinar discussion today. I'd like to reflect on our previous webinar that was called Data Collection for Effective Underground Asset Management. This was a joint webinar conducted with HBK Engineering to help address our aging underground infrastructure. The main points of that webinar started with collection of viable data with a consistent, repeatable process focusing on the capture of relevant, normalized information about underground electrical networks. This data then was connected to GIS-linked databases to house spatially accurate, critical utility infrastructure characteristics and provide analysis capability. This infrastructure data would then lead to the ability to plan corrective action, replacement, and remediation programs. But the most important part of that webinar is based by documenting and understanding your infrastructure's current state at a given point in time. Let's start with a poll question to ground ourselves and understand where the participants are today to our 2 webinars. For our first poll question, I'll hand this back over to Chrissy.
All right, we just want to know today, did you attend the Novinium in HBK webinar Data Collection for Effective Underground Asset Management performed on August 22nd? I'll give everyone just a few seconds to answer. And I'll be closing the poll.
Hey, thanks, Chrissy. The reason for doing this poll is to understand who might have attended the last webinar and content level the conversation going forward. So thank you for participating in this poll. And hopefully, for those of you that didn't attend the last webinar, you'll see some new information that will come out in this one. Today's webinar is to take this one step further. We want to couple this risk mitigation with real-time remote monitoring of a predetermined set of environmental data to further mitigate risk in your underground electrical infrastructure. What we want you to learn today is simple. We want to take you back to your infrastructure by providing real-time visibility to your environment. You may be asking why. We'll start with explaining what happens in this environment and extrapolate that into a couple of real-life examples. Like most continuous improvement opportunities, we need to have a compelling reason. We want to provide some tools that will change how you manage your assets. Once you have insight to this environment, your actions will be different because you'll have new data that represents underground electrical network environments. Like all improvements to how we do things, we need new tools. Let's start by talking about why do manhole events happen. To start that conversation, I'll hand this off to Lee Getzwich to lead us in that conversation.
Thanks, Branko. So as you mentioned, we're just going to do a little quick review of how these events manifest themselves in the first place. In a large percentage of these situations, especially in secondary networks, the primary culprit is combustible gas. Gas gets generated, it builds up, ignites, and causes an explosion. So how does this happen? Why does this happen? Well, one of the more common scenarios starts with an electrical failure. Our infrastructure is aging. Years of thermal cycling has caused insulation and sheathing materials to start to break down. They form micro cracks. Now, this in itself might not pose an immediate problem, and in fact can go undetected for years, especially in these low voltage systems. However, when it gets introduced to a conductive media, such as salt water from winter road runoff, that can provide the catalyst that leads to the tracking, arcing, and eventual electrical failure. Now, when these electrical failures occur, the heat that gets generated in the resulting fires causes the polymers and the insulation materials to break down and begin to evolve gases. Now, there's been a lot of study done on the composition of what these gases are that get evolved due to this thermal breakdown. In fact, Steve Boggs did a tremendous amount of work on this, and what he found was that in an air environment, the constituents of thermal decomposition of the polymers consist largely of benign substances, and benign from a combustion standpoint, largely composed of water vapor, carbon dioxide. These are a large percentage of the gases that get generated. However, the same thermal breakdown in an anaerobic environment or oxygen-free environment, the gases that get generated are quite different. In this case, a much larger percentage of what gets evolved consists of combustible gases, such as hydrogen and carbon monoxide. So referring back to our graphic here, when you see we have the case of an electrical fire occurring on a cable within a conduit, any oxygen that's present in that confined space will quickly get consumed by the fire. We now have an anaerobic condition. The heat from this electrical fire continues to break down the insulation materials, gas gets generated and flows down through the conduit and then enters into the manhole space. Now, this is just one mechanism by which combustible gases can enter into a manhole space. Other scenarios could be adjacent natural gas lines, where a line might fail, form a leak, the gas permeates out and propagates through the substrate and enters the vault through cracks or holes in the concrete structure. Very much like steam lines, and many of you, I'm sure, have dealt with steam holes in your networks where an adjacent steam line has failed, the steam migrates and starts coming out through your manhole. Same type of mechanism. Organic matter decay is another possibility. Matter builds up, breaks down, and then gases get generated and evolve, such as methane. Or it could be an adjacent sewer line where the structural integrity of the line has been compromised and gases are allowed to migrate through the substrate and enter into the manhole space. The other side effect of organic matter could also not necessarily be combustibles, but toxics. Toxic gases such as hydrogen sulfide can be generated from organic matter decaying in a manhole space. So whatever the mechanism, these gases get generated, they flow into the manhole structure, and they begin to accumulate. Now, it's very important to point out that this gas accumulation can occur over the course of several minutes or the course of several weeks. We mentioned earlier that the two primary combustible gases generated during an electrical fire are hydrogen and carbon monoxide. And while hydrogen is highly combustible, it's also highly mobile. It tends to disassociate very quickly and tends to resist building up over long periods of time. Carbon monoxide, not so much. It is roughly the same density of air, and it tends to stick around and accumulate in spaces that have limited gas egress, such as a manhole enclosure. Now, we've done studies here at Novinium on the decay rates of gases in manhole enclosures, and what we found is that in an enclosed manhole space, it can take several days for a concentration of gas to dissipate down to levels below the lower explosive limit of some of these combustibles that we know can be present. And what's important to mention that in these experiments, we did not take into account an original source of generation of the gases we were measuring. These were static experiments measuring natural decay of a predetermined concentration of gas. In the real world, we know these gases are coming from some source somewhere. So what we conclude from this is that it does not take a tremendously high rate of gas generation for it to potentially build up to a point where it reaches explosive levels. So now we have combustible gases accumulating in the manhole. The manhole originally was full of air. It is no longer an anaerobic environment. We have two legs of the three legs of the combustion triangle present, fuel and oxygen. And all we need now is that third leg, an ignition source. This ignition source can come from anywhere. Could be the original electrical fire propagating down the conduit until it reaches the manhole. It could be some other electrical anomaly within the manhole that generates a spark. Could be a guy throwing his lit cigarette down the manhole. Whatever the source, the third leg of the triangle is now complete. We have combustion, deflagration, and subsequently a manhole explosion. So that's a little overview behind the theory of what the conditions are that lead to the development of these events. And up next, Branko is going to take you through how in the real world these events affect your businesses, your customers, and your communities. And just as a quick reminder, if you do have questions, please feel free to submit them at any time throughout the presentation via the chat window. But before I turn the reins over to Branko, I'm going to turn it over to Chrissy, who has our second poll question for you.
Our next question asks, what causes of manhole events are of the most concern to you? Please choose all that apply. And I'll give everyone a few more seconds to answer this question. People are still voting, so I'll wait a little bit longer. Okay, and I'll be closing the poll.
Okay. Looks like many of you are concerned with the flammable gases, as you are concerned with primary cable failure, a very different mechanism of failure, one that tends not to build up slowly over time. Primary cables tend to fail relatively instantaneously when they do. Certainly VOCs and other issues are of a concern as well. So it's good to know what you folks are interested in seeing, and we certainly have some more subject matter to talk about that. And with that, I am going to turn it over to Branko.
Thanks, Lee. Lee has given us a little insight to how these events occur. Let's put this into the next level of perspective. Through studies and data, we predict that there's probably 3,000 plus events per year in North America. These events are defined as fires, smoking manholes, and dramatic explosions. These events are those that are captured through media and from customer interviews. There are lots of events that never get recorded because they either were not severe enough or the event itself didn't disrupt the public to make any news headlines. Though salt is a major enabler to the whole process of gas generation, we want to make clear that these events are not just centered around areas where salt is most common. Events occur for all kinds of reasons, and we should make the statement that frequency event is probably different from region to region, but events occur in most geographies to a certain degree. Let's examine a couple real-life examples. In August of this year, an event occurred in the Greektown area of Detroit, Michigan. For those not familiar with this area of Detroit, it is an entertainment district full of people, restaurants, hotels, and social gathering places. As you can see from the pictures, there was dramatic disruption to the area, and there was some infrastructure damage. About 4 manhole covers went flying in the air. Police were present and directed people away from this area, which is typically full of people. Luckily, no one was hurt by the event. In our modern day, we have lots of tweets that can add to the story. There were localized evacuations. People were stuck in restaurants and told to stay in place. In some cases, information being told was inaccurate, like is mentioned in the right tweet about an elevator explosion. The part of the story that is not told but can be evident are the costs associated with these types of events. There are the costs to the establishments in the area because they cannot provide service. The police and fire department were on site. Inevitably, the utility was on site to determine what happened. Think of the costs associated with this disruption. There has to be a better way in our modern age to mitigate these events so they are less disruptive and common. Here's another example. These pictures are from Hyde Park in California. There was a major explosion that occurred here as evident in the pictures. There was a large amount of energy released during this explosion. A restrained manhole cover would not have prevented the destruction and the possible harm that could have been done to people and property. This explosion occurred at 3:30 p.m. in the afternoon. Now, this was September, and fortunately, children were probably not returning from school yet. Luckily, no one got hurt, but damage was done to the roadway, the neighboring cars, and the underground infrastructure was destroyed. These tweets tell a little more of the story. 3 vehicles were damaged. Natural gas was detected after the explosion. The natural gas line was probably damaged because of the explosion. Again, think of the associated costs of the roadway, the community, personal property, which is the cars, and the underground infrastructure. There are both direct and indirect costs here. As a utility, you probably don't plan in your budget's investments the funding to replace this manhole and its associated underground infrastructure. The main point to be made here is that these costs are not predicted and funded. The other main point is that in our modern age, we have tools that can make communities safer and our electrical grids more reliable. We now want to dive into tools that give you a better insight so that you can be proactive about looking and analyzing this environment. But before we dive into a solution, we want to connect us through a simple analogy. I remember back in the 1970s when maybe having an engine light of any sort was novel and new. Today we have lots of information hitting us in the everyday vehicles we drive. I want you to keep the check engine light in the back of your mind. When we have a light come up in our cars, it is up to us to address the alarm so that we can stay safe and keep our cars reliable. In today's car, we have 100 times more information than the cars of the 1970s. This means that we have evolved the check engine light to make our cars more reliable and safe. Why wouldn't you apply the same principle to our underground electrical infrastructure? If our car overheats, the check engine light appears. Imagine if you had indicators that describe the heat being created in parts of your network that could lead to gas generation. When we run out of fluids in our cars, we address them. Why wouldn't you want to know if gas is being created in your manhole systems? We'll reflect on the check engine light as we talk about providing indicators to you about your underground infrastructure environment. We need check engine lights to keep our electrical grid safe and reliable. Wouldn't you want to know before this happened to you? If we don't address the check engine light, well, the picture tells a story. Similar to Greektown and Hyde Park incidences, we have events that turn into destruction of infrastructure, personal property, and hopefully not injury to a person. We now want to explore the mechanisms that can be deployed in your underground electrical infrastructure that would be analogous to the check engine light. With that said, Lee will start the journey to explain how a check engine light can be used to address environmental underground electrical infrastructure concerns. With that, I send it over to Lee again.
All right. Thanks again, Bronco. As he mentioned, wouldn't you want to know? Well, what we're going to talk about now is what we call the total prevent solution. This is a holistic approach that addresses the root causes that lead to the development of the manhole events that we talked about earlier, instead of just mitigating their consequences when they do occur. This total solution starts with the prevention of that catalyst I mentioned that exacerbates the problem of electrical failure in the networks. Figuratively, of course, that's saltwater runoff. In the lower left-hand corner, you'll see the prevent vented cover. It's designed specifically to allow for active ventilation of the manhole space while simultaneously preventing road runoff from freely entering into the enclosure. It has a dome design with dam slots that effectively divert any runoff around the cover instead of allowing it to freely pour into the manhole through the events. The second element in the center is the ventilation unit. We know that with many different sources of gases, it's not always possible to prevent gases from entering into the enclosure. But what we can do is keep them from building up and reaching that explosive level. Active ventilation does this. It circulates fresh air into the enclosure while venting out any combustibles to the atmosphere before they can reach any levels which are dangerous to the system. And then next, on the right-hand side, the next two components of this total solution, and what we're really here to focus on and talk about a lot more today in detail, are real-time monitoring and data analytics. The unit on top, the smart monitor, measures different gas levels, temperatures, and other parameters that allow you to see what's going on in real time within your manhole environments. And the data analytics, which Branko is going to talk about in much more depth in just a little bit, allows you to establish benchmarks and see trends that can indicate changes occurring within your system over time. So this is a view of the underside of the smart monitor control box. And the first thing that's important to point out here is that this unit is designed for robustness. We know manhole events are a challenging place to be for electronics. So we took great pains to assure that this unit can survive in these nasty environments. The first thing I'd want you to take a look at is this enclosure is designed to be an airtight bell configuration. As I mentioned before, we're looking at the bottom of the control panel so that when these manholes flood, which we know they are going to do, it creates an air pocket, and that prevents the water level from ever reaching any of these sensor connection ports. Now, these sensor connection ports you're seeing are all rated IP68, so it's an IP68 rated enclosure. Even so, it's designed to survive up to 15 feet of submersion for extended period of time without the water level ever reaching or touching any of those connection points. Robustness is also about redundancy, doubling your level of protection. Now, looking at the specific components of their monitor, you'll see there's an internal plenum where there is an array of gas sensors. Now, included in this default package of gas sensors are ones that measure oxygen, carbon monoxide, methane, also temperature, relative humidity. And it's also important to point out that this system is fully customizable. Other sensor options are available, such as hydrogen sulfide, carbon dioxide, redundant carbon monoxide, if that's important to you. Whatever is important to your utility and your particular application, the unit can be customized to address those particular concerns. So in addition to the internal gas sensors, there are several external gas sensors available on the unit. It has 3 external temperature sensors, which can be positioned strategically throughout your vault enclosure. It has a water level sensor, which will tell you how much water is built up in your manhole at any given time. There is a float switch. Again, redundancy, protection. The float switch is designed to trigger that when the water reaches a certain level, it will turn off the internal air sampling fan that draws air into the gas sensors, and that is another level of protection to prevent the fan from drawing water into the control box should it be running during a flooding event. And then finally, the unit is also equipped with a mass airflow sensor input. If your unit is installed in conjunction with a ventilation unit, the mass airflow sensor can monitor the output and performance of your ventilator and let you know if you've got anything going on, such as a blockage, or perhaps somebody decided they wanted to take a nap on top of the manhole and you're losing your airflow. You can go sense that and have someone come take care of it. So this next slide shows a good example of an installation inside an actual manhole. And what we like to point out here is the flexibility of the system. The unit mounted up on the wall can be positioned anywhere within the vault structure or even suspended from the roof as long as you're using L brackets to maintain that vertical orientation to take advantage of the bell design. Now the unit there mounted on the wall is going to have your air intake and venting filters where you're air sampling fan is drawing in air from the vault structure, taking your gas readings, transmitting them to the web portal, and then ventilating that air out. Of course, stainless steel air filters prevent dust, debris, other gunk from getting in there, as well as bugs and critters and anything else that wants to go find a nice warm home. In addition to the unit itself, the external sensors, again, flexibility is what the system is all about. The thermocouples can be positioned wherever you feel is most appropriate for this particular application. In the case shown here with the yellow arrows, you might want to put one on a particular power line that you might have some concerns with. Perhaps there's a splice in there that you want to keep an eye on. You can position one there. Green arrows are another thermocouple line that could, for example, be positioned down into one of the conduits that you might have a concern with of something going on further down the line. And a third sensor placed somewhere randomly within the structure to give you that ambient atmospheric reading of what's going on. What's really important about these three different sensor locations isn't so much the readings that you're seeing in real time, but the relativity to each other. If you have a manhole structure that is at a certain temperature, that's great, whatever it's at, but if you happen to have a sensor in front of a conduit and you're getting a 20-degree differential temperature reading, that could be an indication that something else is going on besides it just being a hot day outside. So in addition to the thermocouples, we have our level sensor. Tells you, positioned here, shows you it's positioned down here, of course, at floor level. Tells you how much water is building up with your enclosure, within your enclosure. This is also very powerful data to have, not only to know whether or not you've got conduits that are filled with water, and if it's winter time and you've had a snow event, you might even be concerned about salt water having gotten in from some other point. But this could also be a powerful tool for scheduling and planning your crews. If you have a manhole that you know has 8 feet of water in it, you might want to schedule your vac truck to come out and pump that water out ahead of time, rather than having a crew of workers standing around watching water pour out of a spout. And then, of course, the float switch. Again, strategically placed that when water reaches a certain level, it shuts off the internal sampling fan so you're not drawing water into the unit. Your signal will also go out that tells you that the float switch has been tripped, so that will also be an indicator that your gas sensors are not going to be providing data that's actual gas from within the vault. So you'll be able to see that my float sensor's tripped, I've got a lot of water in there, and we need to either address that or not worry about it filling up with gases. So just to recap some of these design benefits of a system like this. Again, first is reliability. Reliability and robustness. It's designed to be able to withstand and survive in these environments. The rough environments of manholes, flooding events. It is designed to continuously provide real-time data back to you regardless of what's going on in the system. The system is also flexible. It's flexible from the standpoint of its installation, of where you can place sensors, how you can configure it to maximize its value to that particular application. It's also flexible in its configuration, whether or not you're interested in certain types of gases, certain types of sensors, whether it's airflow or toxic fumes. It can be fully customizable to fit your specific needs. And then one of the real important benefits, and Branko's going to talk a lot more about this in a second, is the real-time data. Not only does this provide you the ability to see what's going on in your manhole in real time without having to go out, pull a cover, stop traffic, and get down in there. You can see what's happening, see the conditions. But in addition to that, in addition to the real-time data, it will also provide you historic data. The historic data that allows you to track trends and understand how things are changing over time in your system. And those pieces of analytical data can be very powerful in determining whether or not something is going on that you should be concerned with. And with that, I will turn it back over to Branko to talk more about the data analytics.
Thanks, Lee. Lee has taken us through the devices that can lead to the check engine light. Just like our cars, devices have to be designed to check the environment. We now want to connect you to that data, which will enable you to make safe and more reliable decisions. So the Novinium Prevent Smart Monitor gathers all this environmental data as Leah shown in the previous section. We need to take this data through a system by communicating it out of the manhole environment through our smart monitor. In our standard offering, we transmit live events through a cellular network so that events are captured and broadcast as live occurrences versus stored data. We then take this data and transform it so that it is useful. We do this to ensure quality while loading it into a secure and reliable source. Next, delivering it to you so that you can make better and more informed decisions. We combine data to create an event history to understanding trending of certain environmental data. We also create visual tools that make it easier for you to navigate the complexities of the data being gathered. The net result is ease of use to the end user. And finally, this data can be sent to you via a web portal on your laptop, iPhone, Samsung, or any tablet. This data then becomes accessible to those people within your organization that could use the data to make better decisions. It is customizable to meet the need of the individual or organization. And most importantly, we know that security is important to utilities, and that is why checks need to be put in place to secure data and make sure it is reliable and accessible. The main takeaway here is really the human interface. By giving you this data, you can make decisions to implement changes in your electrical system before any issues occur. Let's look a little closer to this data and its impact. Every manhole has a check engine light. Well, is more than just a light. It is a data retrieval mechanism that sits within an underground environment that most humans don't enter on a daily basis. This data is geographically based data. This data provides alarm states just like a check engine light would do for your car. You can or could look at various manhole systems and determine if there is a trend occurring. Just remember, this is giving you real-time data. The value is the real-time aspect. Instead of waiting for the impending event, you can proactively investigate and mitigate the risk. Also, metadata can be added so that key characteristics can be attached to each manhole or underground system. With this data, you start the process of making decisions around what can or could be occurring in your underground electrical system. In the Greektown and Hyde Park incidences, we could have had some forewarning to temperatures or gases before the events could occur. Let's dive a little deeper. This real-time data can further be investigated by diving into a specific location. Since it's geographically based data, you could deploy inspection programs based on specific needs versus guessing on focused areas. This data also carries a time element that might also give you a sense of how fast something might be happening. You can view the gases being generated. Specifically, we can look at carbon monoxide, methane, and hydrogen sulfide, just like Lee described in how manhole events occur. We can view temperatures that could strategically be located as described by Lee in the installation of the system. Since it is GIS-type data, you could deploy an inspection program based on specific needs versus guessing on focused areas. Depending on the data, you could dive deeper and look at data over a span of time. This might give you an indication if this is something that just started or is ongoing. It also can tell you trends and magnitudes. Think of the savings and costs by implementing better planning stemming from data. Let's look at a couple more examples. What is unique about gathering data is the simple fact in our modern day we can gather a lot of data and store it. You can look into an environment and investigate data over periods of time. We know that water is an enabler of events in manhole systems. It helps with salt and other contaminants in entering the manhole environment. Some utilities might deploy programs that actively pump water because of systems that might be at risk of an event or other reason. Wouldn't it be beneficial if you could look at a manhole and determine if it needs pumping before you got there? You could deploy your crews and plans based on real-time data. It will help in preparation of going to the manhole site. In fact, if needed, you could look at this data over time to understand how long it does it take to fill with water. Maybe based on the data, you could define how water was entering and what steps could be taken to reduce the water infiltration. Though this is a simple example, it does drive to the fact that data can help you with your decisions on how to address issues and how to utilize resources better. Let's look at one final example. Now, a more serious note is gases. Carbon monoxide is not only dangerous to breathe, but is also very explosive. Based on alarm states on the smart monitor, you could set up levels in which makes you address the issue before it turns into a manhole event, as Lee has described in the previous section. Just remember back to Detroit and Hyde Park in California. What is the benefit of understanding the environment and diagnosing what a combination of temperatures and gases may cause a manhole event? You could look at the data over a period of time. This might help you diagnose if the issue is ongoing or is gas being created at certain times. It leads to cable repair or replacement before an event has enough time to organize itself. Before we conclude this webinar, I want to have one more poll question, and so I will hand this over to Chrissy.
Our final poll question asks, what aspect of the smart monitor solution do you think is most relevant? Please choose all that apply. And I'll give everyone a few more seconds to answer. Okay, and I'll be closing the poll.
Thanks, Chrissy. It looks like 100% of you thought gas sensors are really important, next followed by water level sensors, which kind of confirms what we're seeing in the marketplace today. As we conclude this webinar, this last poll question is pertinent to what is most important to you. I hope that you all learned something new today, and capturing of environmental data is essential. We have not identified the iceberg. There's still more to learn that is underneath the iceberg. What we want you to take away are these key points. Understanding the underground environment will help you be proactive so that you can increase efficiency and quality of services versus reacting to events that could naturally be mitigated with information. In our modern age of data, we are always increasing the amount of data we digest to make better decisions. Data inevitably will make you think differently when it comes to inspection programs and improving assets overall. I know you all heard the term smart cities. I don't know if this is a fad or something bigger. What I do know is that people like innovation. We truly believe that if you have data, that this leads to innovative practices and decision making. Also, think about describing to your customer that by using environmental data, that you are making their services more reliable and better. Now that is innovative. Now the most important part is the check engine light. Well, there's another aspect of the check engine light. Imagine not having any gauges on your car dash. How well could you drive, maintain, and be safe in your car? Real-time data makes us think differently. Let's make sure we are understanding the environmental data of our underground electrical infrastructure. Let's make better decisions. Let's make our electrical grids more reliable. Let's save money and reduce cost. And most importantly, let's keep our people, personnel, and our community safer. I would like to thank Lee Getchwich for his contributions here today in helping us learn about the environment. I also want to thank all of you in attending our webinar. With this conclusion, I hand this back over to Chrissy to help conclude our webinar and to answer some questions.
Thank you, Bronco, and thank you, Lee. At this time, we will move on to the question and answer portion. If you still have questions, please feel free to enter them into the chat window, and we will address them. We have received some questions from our audience. The first one asks, what do the colors mean on the Smart Monitor web portal?
Yeah, I'll take that question, Chrissy. The colors on the Smart Monitor, the deep reds are warning states. Basically, are alarm states. When we look at the web portal, we've actually set different states, and these are all predetermined levels of measurement that we would work with our utility partners in this. Some of the other colors that would be on there would be orange, which means maybe there's a car parked over a smart monitor. What's unique about the smart monitor too is we never lose data. The data is always being stored on an SD card so that the data can be retrieved later once we have communication reestablished. So the colors do have meaning, and the colors are meaning that's attached to actual levels we would set up with the utility and setting the levels they want to be measuring.
Thank you, Bronco. Our next question asks, does your system provide security options?
Yeah, so security is kind of an interesting question because it's probably dependent on what the needs are of the utility. And I'll answer the question two ways. One is the way we have it set up right now with our web portal, we do end-to-end encryption. Think of this as any other software as a service company like Salesforce or even some banking institutions where for somebody else to access your data, they have to have your password or some kind of decryption code to get into that data. So what we do is we work with the utilities to make sure that their data is secure from end to end on the data that's coming from our monitor. The other question that gets asked once in a while is security when it's in relation to the manhole itself. Though we do not provide necessarily a solution to this, we do provide a platform that could evolve to this. And so if somebody wanted to enter a manhole, I know that in certain situations, manholes have to be secured because of the presidents in town or some main event. Could we provide some kind of mechanism that works through our platform? Possibly. We have a mechanism that transmits data out of a manhole. So once we have that platform, working towards solutions where we create that type of security could also be feasible.
Thank you, Bronco. Our next question asks, do you recommend to install on each manhole or manholes with primary cable?
Thanks, Chrissy. I'll take this one. We recommend you install the smart monitor on any manhole where there is a particular concern that there might be gas buildup. Certainly, whether or not there are primary cables in there doesn't really change the fact that gas generation can happen. It's the secondary systems, the lower voltage systems, that are more prone to seeing the slow buildup of gases due to some of these failure mechanisms we were talking about earlier, where the arcing and carbonization and thermal breakdown of the insulation materials, as I said, they can go relatively undetected for long periods of time, but they can also be generating very, very small amounts of gas that just slowly collect in those systems. So those systems may have primary cables also running through them, or they may not. So any system where you feel you have a potential concern, we would recommend installing a smart monitor.
Yeah, if I could add to that, Lee, I think, the smart monitor is an environmental monitor. Even though right now we probably focus on secondary networks, it can pretty much be applied in any type of environment where we're looking for gases, we're looking for temperature gradients, things like that could add to understanding the environmental data of that environment. So just to keep that in the back of our mind that there's other factors that come into consideration here when we look at applying a smart monitor.
Thanks, Lee and Bronco. Our next question asks, how do you test the accuracy of your sensors?
Yeah, all our sensors are fully evaluated in our lab here at Novinium. They are run through a series of experiments using highly accurate calibrated gases, and every one is calibrated after it's received here. And again, we've also done extensive testing, longer-term testing on these sensors, whether or not it's in rough environments, multiple or long-term measuring excessive levels of gases. For example, carbon monoxide will go up to 100% to make sure that we're not going to oversaturate or cause any drift within the sensors. So we do have a fairly extensive testing protocol to make sure that the sensors are providing accurate data.
Thank you, Lee. Our next question is, what is the expected lifespan for the sensors?
Well, again, this unit is designed for robustness. All of our sensors are IR type. They're not reliant upon any sort of chemical reaction to detect the different levels of gas. So therefore, the theoretical life of the sensors is infinite. We do put them through a robust environmental testing protocol to evaluate them in terms of the different environmental conditions, whether it's heat, humidity, and some of the other things we're going to see, excessive levels of gas they might see, other gases that aren't necessarily to be measured, whether it's gasoline vapors or things like that. So the expected lifespan the system itself is designed to last at least 10 years before it requires any maintenance or reevaluation. So that's how we go about making sure that the sensors are going to work.
Yeah, I would like to add to Lee's comment. There's lots of things that we consider when we look at the smart monitor. We also have deployed devices in our smart monitor to do condensation control within the monitor. The other thing too is our sensors are not continuous. We're not running them continuous duty. We're also doing intermittent duty on the sensors. So also Lee mentioned earlier on in the presentation about the float switch. We also don't want to put any undue stresses on the sensors by drawing in water or anything like that. So we looked at this as a holistic approach to the smart monitor to make sure that we're basically touching on all the things that could harm the sensors or things that we can mitigate by just simply through firmware or through other devices, create that environment so the sensors can live for a long period of time.
All right, thank you. Our next question is the data backed up in real time as well?
Yeah, so the data is backed up. So what's interesting, even though we always talk about live events, we are transmitting live events to a web portal to the human being. Now, we mentioned earlier that maybe if a car or something inhibited the communication, that we don't lose data. So every smart monitor has an SD card that can hold up to 5 years worth of data. So the data is being stored. Also, when the data is going through our system, it could be stored on an SQL server or somewhere else. So the data does have redundancy so that if something were to happen, we have that data stored somewhere. And so the answer to the question is, yeah, there's multiple layers of redundancy here.
Okay, thank you, Bronco. Our next question asks, how is data transmitted from the smart monitor to the web portal?
Yeah, with our current method of transmission is we use a cellular network. We use a GSM signal to be able to get the data out of the smart monitor to a cloud-based service to a SQL server, and then we basically take that data and we transform that into what we call the web portal, and that's how you get your data. We realize that utilities have different needs of how they get data to them, and I think we have our standard offering, but we would be working with any kind of utility if they wanted to go through their servers or something like that, but we would work through that to make sure that we get the data to them in the most secure and reliable fashion that works for them.
Yeah, Bronco, and just to add on to that a little bit, I also want to point out that the the prevent cover, the vented cover that we've designed to go work in conjunction with the system, was also specifically designed to allow the transmission of cellular signals through it. So it is essentially transparent to the cell signal. That's why we're confident we're able to get cellular signal out of a manhole.
Thank you. Our next question asks, what is the average price per unit?
So that's a hard question to answer on a webinar, but I'll answer it this way. If we look at smart monitors in the market today, handheld or otherwise, they can range anywhere from $2,000 to $10,000. Depending on the needs of our customers in the market, we're probably going to be in that same range to be able to provide that type of service to the customer.
Thank you. And we have time for one more question. This question asks, does Novinium have access to all of the data, or is it secure within our organization system only?
Yeah, the answer to that question is, just like we mentioned, we do the end-to-end encryption. Depending on the need of the utility customer, we could put in basically measures that allow only the utility to look at that data, and then only time we could look at the data if we were given a decryption code from that utility to go look at that data.
All right. Thank you so much, Bronco and Lee, for taking the time to speak with us today, and thanks to everyone for joining us. If we didn't get to one of your questions today at some point, we will make sure to reach out to you individually to make sure your question gets answered. As the webinar concludes, please take time to complete the survey at the end. We value your feedback and your comments greatly, not only on the webinar, but on the Smart Monitor itself. I hope you enjoyed today's webinar, and we'll see you next time. Thank you.
Thank you.